This is the first lesson in Unit 4 for data management. Unit 4 is called Discrete Probability Distributions. And the emphasis is going to be on discrete, the term discrete, because later on we're going to talk about continuous probability distributions in another unit. So just a little bit of a look ahead at this unit. The first topic is what a probability distribution is. Sort of define that and give you some examples on how we can use that. And then the rest of the unit, the other lessons, are some specific types of discrete probability distributions. We'll look at uniform distribution, binomial distribution, geometric distribution, and hypergeometric distribution. So each one of those will be a separate lesson. So first you need to know what a probability distribution is, and that's what today's lesson is going to be about. So the first definition, a probability distribution is the probabilities for all possible outcomes of an experiment or sample space. All right? So it's all probabilities, or probabilities for all possible outcomes. All right? So it's not just one probability, it's all of them considered together. So again, once we do an example, then I'll be able to talk a bit more about that. But we're taking probability not just of one thing, but of two or three or whatever, however many possible outcomes there are. A random variable is a quantity that can have a range of values. It's designated by a capital X, with individual values designated by lowercase x. So overall, we're going to let the letter X represent our random variable. Okay, so it can have a range of values. And again, to have a distribution, the idea is that we're going to have more than one possible value. A discrete random variable is a variable that can have only certain values within a given range, such as the sum of two dice. We've seen that when we roll two dice, then we can roll a 2, a 3, a 4, and so on up to a 12. So we can't roll a 1 if we roll two dice. We can't roll a 13. So a discrete random variable is one that has certain possible outcomes. All right? And again, the probability distribution then would be, what's the probability of getting a 2 if we roll two dice, or getting a 3, or getting a 4, and so on. A continuous random variable, which is not what we're going to look at in this unit, but we will look at later, is a variable that can have infinite number of values within a given range, often measurements such as volume or time. If you think back to what you've learned in earlier grades, probably grade 9, you learned the difference between a discrete variable and a continuous variable back then. In a more simplistic way, you'd look at things like number of cars in a parking lot. That would be a discrete variable. You can count it on your fingers. Whereas a continuous variable is something that can be broken up into smaller and smaller intervals, and it makes sense, like, once again, volume or time. So we're not going to be focused on that in this unit, but it is something we're going to look ahead to. And finally, a probability histogram is a graph. It's a graph of a probability distribution in which equal intervals are marked on the horizontal axis, and their probabilities are indicated by the area of the bars. So it's going to look like a bar graph. There's a few things that'll make it a histogram stand out, or to mark it as a histogram as opposed to a bar graph. And those things are, for example, the idea that they are equal intervals. That's important. So each bar has a certain interval it covers. That's on the horizontal axis. And then again, it's the probabilities are indicated by the areas of the bars. Also, for histogram, the bars are all touching each other to represent the fact that they're sort of covering all the spaces and there's no gaps in between them. All right, so we're going to talk a lot about histograms over the next little bit as well. So with examples, then it should become pretty clear. All right, so here are some examples. The first one is a table that gives the percentage breakdown of the number of rooms in an apartment or in apartments in a particular complex. So imagine an apartment building. It's got some 2-bedroom apartments, some 3-bedroom apartments, 4, 5, 6-bedroom apartments. That's what's in the left-hand column of this table. In the right-hand column, it says percent. So what you're being told is in this particular apartment building, 15% of the apartments are 2-bedroom, and 30% are 3-bedroom, and so on. All right. Notice how if you add up all the percents, 15 plus 30 plus 42, that equals 87 plus 10 plus 3 is 100%, because things have to add up to 100%. Right, so that's something we always want to check out for, or that things are adding up to the expected amounts. Identify the random variable. Is it discrete or is it continuous? So, well, the random variable is the number of rooms in the apartments. So again, we can have different possibilities. Some of them are 2 rooms, some of them are 3 rooms, and so on. But that's what we're looking at, the number of rooms. So x equals the number of rooms. And deciding whether it's discrete or continuous, again, can we count the number of rooms on our finger? Are they specific things? Are there a finite number of them? And yeah, of course. You can have 2 rooms, or you can have 3 rooms, or 4 or 5 or 6, but you wouldn't have a 2.5 bedroom apartment. You wouldn't have a any decimals other than that. So that's something that is discrete in that case. Again, if I could break it down, it would be continuous. All right, so we want to construct a probability histogram. So that's what the grid is there for on the bottom. So remember, for the probability histogram, we've got equal intervals on the horizontal axis. In this case, because it's discrete, the intervals will just be the number of rooms. Okay, so we're going to have x on the horizontal axis. And just to make the best use of this space, I'll use 2 grid lines for each one. So I'll put a 2 here, 3, 4, 5, and 6 like this. And then I'll create bars above those. And then up the vertical axis, we'll have p at x, which is just the probability, well, it's the percent of apartments that have these different number of rooms, but that's also going to be the probability, right? Because if, say, 15% of the apartments are 2-bedroom apartments, that means if I was to randomly select an apartment in this building without knowing anything about it, I would have a 15% probability of pulling a 2-room apartment number out of a hat, right? So percent of apartments is going to be the same as the probability. And so the percent is going to, I'll write that as a decimal. And so the highest percent is 42%. So as long as I got enough room for that, then I can maximize the use of my scale. So I'll maybe do 0.1, which is 10%, and 20%, and so on like this. And the way that I create my probability distribution is then I create bars that go up to the appropriate height. So a 15% for 2-bedroom apartments would start here, and it would go up to this high. All right, so that's going up to halfway between 0.1 and 0.2 on the probability, and it's a bar above the 2. And then for 30% for 3-bedroom, that would be like this. And so that's pretty easy to do, as long as you understand the basic concept. I'm trying to be as accurate as I can, but I'm not worrying about being perfect. So that's what my probability histogram looks like. sometimes we connect, sometimes what we'll do is we'll put a dot in the middle of each of the bars, which I'm going to do right now just to show you how it works. So if I put a dot here in each of the bars and then connect those up, so I'll start down at the corner here and I'll just draw some straight lines to connect these. That's called a probability polygon. So it just creates this shape that it gives us the shape of the distribution. As you can see by looking at this red line I've drawn, the probability polygon, it sort of has most of the area under the bar, inside the bars, towards the left-hand side. It tails off a little bit towards the right, and so that is called a right-skewed distribution, which is actually the answer to D part here. I'll come back and fill in C in a second, but part D says describe the distribution. Well, this is a right-skewed distribution. Right-skewed means that it has a tail on the right-hand side. So right-skewed distributions always follow a shape that's sort of like this. Pardon my shakiness with the Apple Pencil there, but what I'm trying to show is that it's got the highest point more towards the left and it tails off towards the right. And in fact, we would call this the tail here. So if something's right-skewed, it's got its tail on the right-hand side. If it's left-skewed, then it'd be a mirror image of that with the tail on the left-hand side. So to go back to C part, though, explain the meaning of the individual bars in the histogram. The height or the area of each bar represents the corresponding probability of randomly choosing that size of apartment. So a quick look at the graph, if I didn't have the table ahead of time, is I can see that most of the bedrooms, most of the apartments are a 4-bedroom. I would have the highest probability of randomly selecting a 4-bedroom apartment if I just drew a name from a hat and so on. Calculate the sum of the probabilities of the distribution. Well, I sort of did that already, but when I was first talking about the table, but let's just write it out here. So if I add together all the probabilities, so we have the probability of a 2-bedroom was 0.15, and a 3-bedroom was 0.3, and so on. If I add all of those up, it equals 1, which is the same as 100%. So that's a probability distribution. So again, it's a distribution because it shows all the possible outcomes. So in this case, there were 5 different outcomes. A 2-bedroom, 3-bedroom, 4-bedroom, 5-bedroom, or 6-bedroom apartment. That's 5 outcomes. And it shows the probabilities associated with each one, and it covers all of them. So it's 5 different probabilities that adds up to 100% probability. If I was to draw a random apartment out of a hat, then I have 100% probability of getting one of those 5 types of bedrooms. All right, the next part. What we can see is that we're always going to have all our probabilities add up to 1 because they always have to add up to 100%. Right? And that's all that this is showing here. So P at x1, remember little x1 just indicates one of the outcomes, and P at x2 is a different outcome, and so on. So however many outcomes you have up to xn, when you add them all up, it's always going to equal 1. Expected value, we've talked about this a bit before in the course. Remember, expected value, or expectation as it's sometimes called, is a weighted average of the random variable. So it's well, let's look at the formula first, and then we'll talk about, I guess, some more specifics here. But so it's a weighted average of the random variable. So the random variable has a number assigned to it. In this case, for the number of rooms, then the random variable is 2, 3, 4, 5, or 6, right? And then we multiply each of those individual random variables times the probability of them happening. That's the p at x1 and p at x2 and so on, you can see in this formula. And when you add it all up, multiply them together, add them up, then you'll get the expected value. It's a weighted average. Again, this will make some more sense once we use it in a formula or use it in an example. What you can see here, this funny looking symbol here, this one, is just summarizing what's right above here. This means the exact same thing. So that big letter there that sort of looks like an E is called sigma. It's a Greek letter. And it tells us to add things up. So I equals 1 to the n on the top. It's saying add up all of the x1 times p at x1 plus x2 times p at x2 and so on. So it's just literally, it's a short form for what is right above it, what I've drawn the arrow to. Make a tree diagram, example 2, that shows the probability distribution for the number of girls in a family of 3 children. All right, no problem. We can do that. We've done this type of thing before. We haven't done number of girls in a family. Oh, maybe we have actually, but we definitely have done coin flipping, and number of girls in a family would follow the same sort of tree diagram as the tree diagram for flipping a coin, right? Because when you flip a coin, you have heads or tails. When someone has a child, it can be a boy or a girl. So the tree diagram is going to look exactly the same. You're going to have, for your first child, for a family's first child, they have either a boy or a girl. Those are the two possible outcomes, right? Then they have child number 2. If they had a boy first, well, they still have a boy or a girl for child number 2. If they had a girl first, they have a boy or a girl for child number 2. For number 3, again, it's just going to carry on. If they had 2 boys, well, they still have boy or girl as their outcome. If they had a boy then a girl, they still have a boy or a girl for child number 3, etc. So we've seen this kind of tree diagram before, and you can quickly check and see that it has 8 outcomes. There's 8 paths, starting with boy, boy, boy on the top, and then boy, boy, girl, and then boy, girl, boy, boy, girl, girl, and so on. There's 8 different paths, 8 different ways this could play out. So that's the tree diagram. All right? So then we want to do the probability distribution. So we want to find the probability distribution for number of girls. So we're looking at the number of girls. So that's our random variable. All right? So the random variable, big X, equals number of girls. So big X, I'll put that in the table. Well, what are our possibilities? If someone has a family has 3 children, they could have no girls, or 1 girl, or 2 girls, or 3 girls. Those are the possible outcomes. What's the probability of each of them? Well, the probability of having no girls, there's only one path that shows no girls. I'll highlight that and then erase it again in a second. This is the one path that shows no girls, right? Remember, there are 8 paths altogether. So the probability of a family having 0 girls is going to be that one path out of the 8 possible. Probability of having 2 girls, jumped ahead, 1 girl, is that path. That path would get us 1 girl. and that path would get us one girl, right? Any of those three paths have exactly one girl on them. Again, there's still 8 paths to choose from, so the probability of having one girl is 3 out of 8. And the probability of having 2 girls, well, now we have this path, we have this path, and we have this path. So again, there's 3 paths that have 2 girls. So 3 out of 8 again. And then that leaves that one path that has 3 girls, 1 out of 8. So if we add up those fractions, that's 8 out of 8, so the probabilities do add up to 100%, or 1. And if we did x times p at x, that's what we could use this table, or this column of the table for, because that'll be helpful for when we want to do expected value. 0, so x dot p at x means x times p at x. So what I'm doing, I'll delete that for a second. What I'm doing is, if I do 0 times 1/8 in that first row, that equals 0. And then if I do 1 times 3/8 for the second row, then I get 3/8. And then if I do 2 times 3/8, I get 6/8, but that reduces to 3/4. And then if I do 3 times 1/8, then I get 3/8. So that's just multiplying the first 2 columns together in each row. All right, so I can use that in a bit to get the expected value. I'll use that when I get down to part C. Make a probability histogram for this distribution. Describe the distribution. Okay, so x, my random variable, is number of girls. So 0, 1, 2, 3. My highest probability is, what, 3/8. So I'm looking at the p at x, the middle column of the table again. So it's 3/8, which is 0.375. So as long as I keep my p at x under 0.4, in other words, make 0.4 fit on there, then I've got enough room on this axis. All right, so then for 1/8, that's 0.125, and so that would be, that's a little low, isn't it? All right, 0.125 would be about here, and 0.375, which is 3/8, would be here, and again, another 3/8 probability for having 2 girls, and then again 1/8 or 0.125 for 3 girls. That's what the probability histogram looks like. If I want to get an idea again of what the probability polygon looks like, then I can connect these and just get the general shape of it. As you can see, it's pretty much symmetrical. It's got the highest point in the middle. That's actually called a normal distribution. And sometimes that's described as a bell curve. And we'll talk more about that in this unit, and also especially when we get to continuous distributions in another unit. Calculate the expected value for the number of girls in a typical family. So remember, in that last column of the table just above where I multiplied things together, that's really my expectation. So it's helping me figure the expectation. So E at x, the expected value for a variable x, remember, is equal to x1 times p at x1 plus x2 times p at x2, and so on. So well, x1 times p at x1 was just 0. That was that top row. And then x2 times p at x2, that was the having one girl times a 3/8 probability of having that, so that was 3/8. And then the next one we had was 3/4, and then the next one we had again was 3/8. So I've already done the work there. I don't have to do it in a table, but that's where it came from. If I add everything together, if I were to get a common denominator of 8, then what I would have is 3, for my numerators, 3 plus 6 plus 3, which would give me 12. So I'd get 12/8 when I add those up. That reduces to 3/2, or 1.5. So what does that mean? Well, in this case, since the random variable is number of girls, the expected value for number of girls in a family of 3 is 1.5. So, again, we have to interpret what this means. Obviously, no family can truly have 1.5 girls. So what this is telling us is that's the average. Again, remember, expected value is a weighted average. So if someone were to do a survey of families with 3 children and find out how many girls they all had, let's say they surveyed 100,000 families, they would find that on average it would be about 1.5 girls. No one family can have 1.5 girls, but on average it's 1.5 girls. That's the expected value. Okay, next example. A hospital is having a fundraising lottery to raise money for cancer research. A ticket costs $10, and 2 million, that shouldn't have a dollar sign in front of it, 2 million tickets are sold or available. There are 4 levels of prizes. There's one $5 million grand prize, there's $300,000 second prizes, and 2,000 free tickets for next year's lottery. What's the expected value for each ticket? Well, it doesn't tell me to make a table, but it's probably a good idea to make a table just like we did above. So first I need to know what my random variable is. And in this case, I'd say the random variable is the payouts. It's the prize amounts. So x is equal to the set of, I'll use set notation, 0 or $10. The $10 is the free ticket, okay? Remember, tickets cost $10, so by winning a free ticket, that's really the exact same as, that's really the exact same as getting a $10 prize, or at least it's equivalent to getting a $10 prize. And then there was 100,000 or 3 $100,000 prizes, and then there's the $5 million prize. All right, so we can make a table up just like we did for the last example. So I'll have a column for x, I'll have a column for p at x, and I'll have a column for x times p at x. And again, we saw that the possible outcomes were losing, winning $0, getting a free ticket, which is the same as $10, getting a $100,000 prize, or getting a $5 million prize. The probability of this happening, of these different things happening is, well, let's leave the losing probability for starters, and just look at the other ones. So there are 2,000 free tickets, so the probability of getting a free ticket would be 2,000 over the 2 million tickets that are sold. And the probability of getting the $100,000 prize is 3 out of 2 million. The probability of getting the grand prize is 1 out of 2 million. So if there were, as you can see, we've accounted for 2,004 of the tickets so far, so anything that isn't one of those ones must be the losing one. So if we take 2 million, subtract the 2004 prize tickets, what we're left is 1,997,996. These are all losing tickets. All right, so those are probabilities. I haven't reduced the fractions in this case, because really all we're looking at is the expected value. So I can do that. I can just do that as a separate calculation. But to get x times p at x, the first one's easy, because 0 times anything is 0. So it doesn't matter how many losing tickets there are. If the payout is 0, then the expected value is 0. If I do 10 times 2,000 over 2 million, then, well, 10 times 2,000 gives me 20,000. Let me see if I can make this a little bigger. 20,000 over 2 million, which reduces, if I were to cancel off a whole bunch of zeros and reduce the 2's, is to 1 over 100. So you get a 1 in 100 chance of getting a free ticket. And then if I do 3 times 100,000 for the numerator, then of course I've got 300,000 on the top here. Which again I could reduce to 3 over 20. And that 5 million times 1 over 2 million gives me 5 million over 2 million. That just reduces to 5 over 2. I don't want to write all those zeros out, so I'll just go straight to the reduced form, 5 over 2. All right, so those are the weighted average for each one of them. So then the expected value is to add all of these up. So once again, e at x is going to be 0 plus 1 over 100 plus 3 over 20 plus 5 over 2. When you type all this in your calculator, and we can just do this as a decimal, then what we get is it equals $2, or I'll add the dollar sign now because that is what it is. It's 2.66 anyway, and I'm adding the dollar sign because we're talking about money in this case. The random variable is monetary amount, so $2.66. So what this is telling us for part B, for explaining the meaning, is you can expect, if you buy a ticket, you can expect that the average winning for every ticket sold is $2.66, which is fine. This is a hospital charity. They're trying to raise money. Remember, the tickets cost $10 each. So if I'm running this hospital charity and I charge $10 per ticket, and I'm paying back an average of $2.66 per ticket, then I'm making a profit of $7.34 per ticket. All right, one more example. Remember earlier in the course, we played a game called High Then Low. This was one where you played against a partner, you drew 2 cards. Was it 2 cards? No, sorry. You rolled 2 dice. And if you rolled a lower number on the second die than on the first die, then you won. And if you rolled a higher or the same number, you lost. If you rolled a 1 on the first die and then rolled a 1 again, then you won the jackpot. All right, so now we're going to use what we've learned about expected value to help us calculate that. I'm going to just do that. I've got this sort of started already, so I'm going to do this on a different hand or a different page that I've already got here. I'll include this, of course, in your notes. So here is a table or a tree diagram that's already been drawn. I think, if I remember, we've already gone through all this. So, but just to remind you of it, it's telling us that, remember that those first branches of the tree diagram, they say have a 1/6 beside each of them because you could roll a 6, or let's just highlight it here. So I could roll a 6 on the first roll, and I've got a 1/6 probability of getting that. Or I could roll a 5, or a 4, 3, 2, or 1. All right? So that's my first roll. Depending on that, then I'll either win or lose depending on what comes next. So if I roll a 6 on the first roll, then 1 through 5 will get me a win. So I've got a 5/6 probability on my second roll to win this game. If I roll a 6, then I lose. So that's where the 1/6 lose comes off of that. And then if I roll a 5 on the first roll, well, my probability of winning goes down to 4/6. And my probability of losing goes up to 2/6. And so as we go down this tree diagram, then you can see the probability of winning goes down for each, the farther down we get, and the probability of losing goes up. And if we have a 1 for that first roll, right down here at the bottom, if we roll a 1, then now our only options are getting the jackpot or else losing. So we still have a 5/6 probability of losing if we get a 2, 3, 4, 5, or 6. But if we roll another 1, double ones, then we will win the jackpot. So at the end of each of these branches, you can see there's 12 branches, because we've again grouped together probabilities. And at the end of each of these branches, you can see an overall probability. So for example, this one here, this top one, if we take the 1/6 in the first branch times 5/6 in the second part of the path, then we get 5/36. That's where there's a 5 in 36 probability of winning by getting a 6 followed by a number lower than 6. And so inside the brackets, each one of those different fractions represents the probability that comes from multiplying the probabilities along the path together. So 1/6 times 1/6 gives us the 1/36th probability of losing in that path there, and so on. All right, so you can see they're all different. I've highlighted all the ways of winning in yellow, or all the probabilities associated with winning in yellow. I've highlighted all the probabilities of losing in green. I guess I missed one of the probabilities of winning. There we go. And then there's, of course, the probability of getting the jackpot, which is a different one altogether. So there's a 1 in 36 probability of getting the jackpot. So those are the probabilities associated with each path. All right, so as far as our probability distribution goes, remember for this game we said that if they win, they would get $5. They'd win $5. If they lose, they'd lose $5. And if they got the jackpot, they'd get $20. So that's our random variables right there. So let's just sort of zoom in on this a bit. So this is the random variable. This is x. Okay? So that's the random variable. So the overall probability, let me switch back to blue for this. So the overall probability of this is p at x for each one of these. So the probability of winning, remember, is if we have these different paths, you could win by rolling a 6 first and then getting something lower, or you could get a 5 first and get something lower, and so on. So you can do all those paths that I've highlighted in yellow, you can do one or the other. So we add those probabilities together. So we're going to add together 5/36 plus 4/36 plus 3/36 and so on. So that's what our overall probability of winning is going to be. So 5/36 plus 4 plus 3 plus 2 plus 1/36. when you put it all together, it comes out as 1536. And that, as a decimal, is 0.416 repeating. So it's about 42% probability of winning this game. As far as losing goes, well, then if I was to add together all those probabilities I've highlighted in green, it's exactly the same, except we've got that extra way of losing if you rolled a 1 first, which is another 536. It's going to end up being, well, let's just go ahead and add them up. So 1 over 36 plus 2 and so on. But then we've got that extra 536 that comes from getting a 1 first. Then we have 20 over 36, which reduces to 0.5 repeating. So 0.55555 and so on. That's what that dot on the top means. It's repeating. So about 56% probability of losing. There's a couple different ways that I could calculate the probability of getting the jackpot. The easiest, of course, is just to do 1 divided by 36, because that's the only fraction. Or I could add the other ones together and subtract them from 1. But anyway, I get 0.027 repeating, or about 3% probability of getting the jackpot. So, again, we take the expected value, and the way we do it is we multiply the random variable times the probability of it happening. So, $5 for winning times 0.416 repeating. Minus $5, losing $5 for losing times 0.5 repeating. And $20 for getting the jackpot times 0.027 repeating. Whoops. And again, we can put that into our calculator, and we get $2.36. Now, again, we have to interpret what this means. It costs $5 to play this game, remember? So if it costs nothing to play this game, then of course it'd be great to get $2.36 on average every time you play, then you'd feel good about it. But if you're paying $5 to play this game, and on average you're getting $2.36 back, you're going to be losing about half your money, slightly more than half your money on average. So this game is not fair. It would be fair if the expected value turned out to be about 0. Okay, that's a pretty long lesson, so I will stop there.